Hello and welcome to the DSA video seminar on implementation of sparse matrix using coordinate list in C. So I'll be your guide on this journey to get a deeper understanding of sparse matrices. So what is a sparse matrix? A sparse matrix is a matrix in which most of the elements are zero. Storing such a matrix in its full and complete form would be memory inefficient, as a large portion of the storage would be dedicated to the storage of zero elements. To overcome this problem, we use sparse matrix in one of the many and numerous different formats, and the format that we are using is called coordinate list format, COO. So what are the advantages of a sparse matrix over a simple matrix? Firstly, it is very memory efficient. By only storing the non-zero elements of the sparse matrix, the amount of memory can be significantly reduced compared to storing the full matrix. The major difference is visible in the case of large matrices, as memory is a finite resource in the practical world. Only in an ideal world is memory an infinite resource. The second advantage of a sparse matrix is computational efficiency. Many sparse matrix algorithms are designed to take advantage of the sparsity in a matrix and can often perform operations on sparse matrices faster than the traditional simple matrices. This again is very important for large matrices, where the number of operations required to process the matrix can be substantial. The third advantage of a sparse matrix is its numerical stability. Many numerical algorithms are more stable when they are working with sparse matrices compared to dense matrices. For example, certain iterative methods for such as solving linear system of equations can converge much faster when applied to a sparse matrix. The fourth advantage of a sparse matrix is its bandwidth reduction. The bandwidth of a matrix is the maximum distance between a non-zero element and its nearest non-zero neighbor, and this bandwidth can be reduced by the use of a sparse matrix. This can lead to a significant reduction in computation time that certain algorithms can easily take the advantage of. This is the sparse matrix implementation in the form of a coordinate list. On the left hand side, you can see a matrix where the first non-zero element occurs at row first and third column, which if we go by zero indexing is the 0th row and the second column. So as you can see over here, at row 0 and column 2 we store the value 3. The next non-zero element occurs at row 0 and column 4, and so at that coordinate position we store the value 4, and so on and so forth. We store the non-zero elements. We only store the non-zero elements. Right now we are not bothering with the zero elements. Now let me dive deep into the code explanation of the sparse matrix implementation using coordinate list. We define two structures here, which basically the first structure is to store the coordinate, which is the single non-zero term, and the second structure here is to store the sparse matrix, which basically contains all the non-zero terms. In the main function of this code, firstly we get the dimensions of the matrix from the user. Secondly, we ask the user how many non-zero elements he wishes to enter, which will obviously be lesser than the product of the row into column of the matrix. Thirdly, we internally allocate the dynamic memory for the sparse matrix, which using this malloc function. And in case there was insufficient memory, we just display the error message and exit the program execution. In the fifth step of the algorithm, we basically ask the user to enter all the non-zero elements in the format x, y value. xy being the coordinates of the non-zero element in the matrix and value being the actual value of the term. In the next step, we display the sparse matrix as if it was a normal matrix with the non-zero and zero elements. We do this with the help of a 3-level deep nested for loop, where the first two for loops iterate through the rows and columns, and the third for loop is used to find the non-zero element. And in the last step, we just display the number of zero and non-zero elements present in the matrix. The number of non-zero elements are given by the user, and the number of zero elements are computed using the product of rows and columns of the matrix minus the number of non-zero elements. And this is the sample input output. Let me show the input output to you more interactively. So we open the terminal, we run the command. Let's enter the dimension of the sparse matrix as 3 into 3, 3 rows, 3 columns. And the number of non-zero elements, let's say 3. Now let me insert the element 1 at the origin. Let me insert the element 2 in the middle of the matrix, and let me insert the element 3 at the bottom right corner of the matrix. As you can see here, this is the matrix, the sparse matrix generated. The top left corner has the value 1, which is the coordinate 0, 0. At coordinate 1, 1, we have 2. At the bottom right corner, that is 2, 2, we have the element 3. The number of non-zero elements for this matrix, sparse matrix, is 3, and number of zero elements is 6. So with this, we come to the end of the working demonstration of the sparse matrix. Thank you for investing your time, and happy coding!